I won't really go very deeply into how this specific zero-knowledge proof scheme works. I'm just going to introduce it briefly so we can kind of reason about what's going on. And then I'm going to go through a couple of different applications or kind of things that we can build right now with the ZK-SNARK circuit that we have. This circuit was made by Kobe, and in here is the GitHub repo. So the idea is that this is kind of a generic circuit that you can use to build SNARK stuff or build privacy systems without having to touch any of the SNARK stuff yourself. So this is like a good kind of entry point to get into know how to use SNARKs for privacy stuff. So that's the first one. And so then because we don't have to touch the SNARK stuff, the major thing that we need to think about is the user interface and the smart contracts. So those are kind of the remaining open problems. So we'll talk about those problems and how to kind of solve them. Then we'll talk about like some of the things that you need to be careful about when you make these privacy solutions. So there's some attacks that just come up over and over again, and you just need to be aware of them. And then talk about future directions, and then we're going to do a demo. But it won't be like a live demo for me, it'll be more like a group demo, that we have a system that's deployed and we want to kind of add a bunch of people to it and play around with it. Yeah, do some tests and see how people use it, whether it's useful or not. Yeah, so that should be fun. Okay, so first, all right, so let's make this like model of a zero-knowledge proof. Okay, so a zero-knowledge proof is you can prove that given a certain set of inputs and some code and some outputs, you can prove that you ran a certain code with certain inputs and got certain outputs. Yeah, and we can do cool things with this. We can hide some of the inputs. We can hide them all. But it doesn't really make sense to hide them all because that doesn't really show you anything. Unless you want to make like binary proofs and prove that I know some information that solves this problem. For example, you could prove that you know the factors of a number. You could prove that you factored a number and things like that. So there's those kind of binary proofs, but really what we want to do is make proofs about more general stuff. So one thing that we wanted that is interesting for us to do is to do a Merkle proof inside a SNARK. The idea here is that A, B, C, and D are some values, and you can make a proof that you know one of those values. But this by itself is not very interesting either, because we want to be able to limit who's able to signal about it. In this situation, people are able to make proofs about being A, B, C, or D. So what if we put some private information here too? What if we have like this kind of public section on the top and this private section on the bottom? So the public section is like, so we have A, B, C, and D, which are public keys. And we have a private key that matches to those public keys. So the idea is that the public keys get accumulated into this Merkle tree, but the private keys are held by each individual. Yeah? So then if you want to be able, so let's put this inside the SNARK, and let's say that, okay, for each of our, now what we do is, for each zero-knowledge proof, we validate a signature, we calculate its public key, and then we prove that that public key is part of this group. Yeah? So we'll have 3 inputs and 2 outputs. So the input is an external nullifier and a signal. So the signal is like what you want to talk about. So in some of our examples, the signal will be just some text, it'll be just some information. In other examples, it'll be like instructions. It'll be like, I want to do this. Yeah? So that's what the signal is. The external nullifier, and this, which is the nullifier here, is something that we developed to prevent like double spends. Yeah, this is a problem that we've had, and the idea is that you can just make the same signal over and over and over again, and no one is able to tell whether you made the signal twice or someone else made the same signal. So this is important to include these external nullifier and this nullifier here, and then the Merkle root. Excuse me. The Merkle root is just a Merkle root. It's like it's the root here. It just defines what the group you're talking about is. Okay. Do I have everyone on so far? Yeah. Okay. Good. So yeah. So for more information on these, like on this technique, there's another talk that you can check out from DevCon. There's a link here. Yeah, and it just gives you like a slower introduction to why we need external nullifiers, why we need nullifiers, and how we can use those. Because we're going to skip over that for the rest of the talk, and if you want to get a better introduction to that, there's this information available. Cool? Okay, so, alright, so far, we've talked about this component here, right? So this doesn't really become useful until we add a few other pieces to it. Okay, so we have this component here, which is our zero knowledge proof. We have our smart contract here, and then we have our user, who has a public key and is able to make proofs. And we have the owner, who's able to control who's able to control this, the A, B, C, and D, the members of our group. Okay, so yeah, so the idea here is that we would make this group with A, B, C, and D public keys, and then anyone in the group is able to make a proof that they are a member of the group without revealing which member they are. And then, okay, so here's kind of the basic infrastructure that we need. Okay, we need a way for someone, the owner, to add an identity to our group. Yeah? So they have this, they can add an identity, they can set the external nullifier, and they can set the gas price, which we'll talk about a little bit later. And then the user is able to do some things too. The user is able to get a list of all the signals that have been made. The user is able to get their path in the Merkle tree so they can make proofs. And the user is able to broadcast a signal and say, this is my signal, show it to everybody. Yeah? And then those people will be able to tell that some member of the group made this signal, but without revealing which member did it. Okay? So there's a problem here. And the problem is where we get to this. Yeah? Because like with the current model of Ethereum, if the user broadcasts if a user broadcasts their own signals, that means that they would have to pay for the gas. And it's easy to track, the blockchain is completely transparent, so you can see who paid for which transactions. And then you'll be able to link transactions together, especially because we, at the moment, don't have a functioning mixer, or don't have a way to get anonymous cryptocurrency in Ethereum. There's some problems like that we need to think about. But even if it wasn't, it's still important that we have a way to sort of hide the gas payer who pays the gas. So the way that we do this is, yeah, so the first one basically says that the users, if they pay for the gas, we can find out who they are. Or we can link signals together, and we can do kind of a meta-analysis to find some things about their addresses. So what we do to overcome this is we have the smart contract refund the gas. Yeah? And then what we can do is we can say to someone else, we can say, will you broadcast this transaction for me? And they can have some cryptographic proof that they'll get a refund for the payments. So we can make this kind of market where people come forward and broadcast their transactions for other people and get refunded. And these people can like make a profit if they want. Yeah, can make a profit. Okay. So deciding who pays for the gas is another problem. It's in some cases we can just have this kind of public contract that people can send money to, and if you send money to it, then that money just goes to pay for gas for other people. Yeah, so if there's some group that you want to support, you can pay for the gas in their smart contract within the signal. Or if we were talking about a mixer, we could take like 1% of the amount being mixed and just set that aside for gas payments. So there's one thing to be a little bit careful about here is that the owner, at least currently, the owner is able to pay for the gas. The owner is able to set the gas price. So the owner can set the gas price, and then they can just set the gas price very high and make a single transaction, and then they will be able to just broadcast that transaction themselves and take all the money. So that's one concern here, but there's some ways that we can overcome this. Okay, and another problem is that we can have kind of, let's say that I want to hire someone to broadcast a transaction, but they broadcast the transaction and hope to get paid, but someone else sees the same transaction and rebroadcasts it with them being paid, the recipient of the funds. This is a problem because that will break like our incentives that we had. So what we can do here to overcome this is we can set the broadcaster as one of the public inputs. So we set the broadcaster, this is the person who paid for the gas. And that gets set at the approve time, so it's dependent, it's up to the user who's allowed to broadcast their transaction. So we set that at approving time, and then the smart contract will only send money to them once the transaction gets mined. Yeah. Okay, so now we're going to go through 3 different sample applications. Yeah, so we're going to talk about 3 different sample applications. The first one is like a journalist who has a bunch of sources, but the sources don't want to, but the sources want to be able to talk anonymously to the journalist. Second one is an anonymous DAO, where you have a DAO that's able to make some decisions about something, how money gets spent or something like that. And we want to be able to do this anonymously. So that's the second one. And the third one is a basic Ethereum mixer. And then there's a whole bunch of other ones that I don't have time to go into, but I have some slides at the end, so if we have extra time, we can go through the slides, or if there's specific questions about that, or about like an anonymous KYC system, we can talk about that in the questions or the time that we have left over at the end. Okay? Okay. All right, so imagine that we have a bunch of people in an organization who are represented by these pictures here, and we have a journalist. And the people in the organization want to give quotes and information to the journalist, but they don't want the journalist to know who they are. But the journalist, in order to be able to publish the information, needs to be sure about that the information is valid, that it came from a certain people. For example, when you read articles, they'll often quote a source as a high-ranking person in some organization. So the idea here, so they need to be able to attribute their quotes to someone in a certain group. So what they can do is, they can contact all of the sources, and they can say, okay, I'm going to make this group for you, and you will be able to make zk-snark proofs that you're a member of the group, and as well as saying something. And then this will be the way that you can send your information to me or to the whole world. You can just broadcast it publicly on the Ethereum chain. So that's what she does. She goes to each of them, and each of them sets up their public key, private key, and they give her the public key. And then she puts the public keys in a smart contract and hashes them all together and makes a Merkle root. Yeah. And now we have this kind of situation here, where the owner is able to, the journalist is able to do a few different things. So the journalist is able to add their public keys to the system, to the group. She just adds their identity. She's able to set the external nullifier. So the external nullifier is to limit the rate at which they can make signals. So she can say, okay, you can make 1 signal every day. And every day she'll update it to, okay, you can do one. In the journalist application, this doesn't really need to be fixed. Because the group is kind of small, there's only 4 people there, and if someone is making a lot of signals, it doesn't really, that's kind of okay. But the important thing about the external nullifier being limited is for the gas refunding. Because if the external nullifier was unbounded, then a single person would be able to make many transactions and just deplete all of the gas in the smart contract. So we have to limit it somewhere. So that's what she does. She just sets an external nullifier, and once every day she updates it. And then she's able to set the max gas price, the max gas price. So imagine that if something happens with Ethereum and the gas price starts to go way up, she can adjust the gas price so that her transactions can still be included, or that her users are still able to broadcast. So anyway, then one of our group from before, one of these 4 people, is then able to make a signal to use a zk-snark to make a proof that they're a member of this group, and to prove and to include some sort of signal with that proof. Yeah, so they create it and then they say broadcast signal. Yeah, they send the broadcast signal, hopefully over Tor, to this server that the journalist maintains. And then the server will then send the signal to a smart contract, which will validate the snark proof and will save it. So that's how this works. That the journalist is able to have her sources, publish information, and send her. So this can work publicly and this can work privately. So yeah, so the journalist could just receive the snarks independently, or you could publish them on a blockchain. So that's one use case. Yeah, so here's one attack that could happen if the journalist was malicious. What the journalist could do is she could reduce the anonymity set. She could just remove people from the set. And when she removes people from the set, if the set is like this, and someone makes a snark proof, we know exactly who made the proof, right? Because there's only one person who's able to make the proofs. Yeah, so this is like one of the major things that you need to worry about, the size of your anonymity set. And if the anonymity set is small, then your privacy is reduced. Another thing that she could do is she could do like a partition attack. She could tell each of her sources, oh look, I have this cool snark system that I use for all my sources. She could put each of the sources in an independent tree. And if they're all in an independent tree, they're the only members in that tree. And the same problem persists, that they have this anonymity set of 1, and the journalist is able to tell who's making which signals. But both of these attacks just degrades the system to the status quo, which is, at the moment, this is how it works anyway. People go to journalists and they give them information, and the journalists publish that information, and they are able to tell someone, oh, this was the source, this is the person who told me this information. But in this case, yeah, so we just kind of degraded the status quo. I mean, it's a problem and it's something we need to be careful about, but it's also at worst, same as the system as it is. Okay? So, yeah, so here's some mitigations for the reduced anonymity set attack. So one thing is that the users could confirm amongst themselves that they are members of this group. So, for example, people could meet each other and say, oh, I joined this journalist group, and they could show the public key, and then each of them could download the tree from the Ethereum main chain and validate that that is the same public key that's included, and then each user will be able to build up a picture of who's in the group. But this will lead to another problem. So maybe I have some more solutions to this. Yeah, so another thing they could do is they could just trust the journalist based upon like previous history or something like that, but I mean, that's not really very good. I mean, that's probably, that will just leave us with a system that's the same as it was before, in the worst case, but hopefully better. Yeah, and so in order to reduce the attacks that they can do here, we can limit the ways the operator can update the state. So if we say that you're not allowed to remove anyone from the group, then that means that the journalists won't be able to take people out, which is good, and they won't be able to kind of reduce the anonymity set after it's been set up, which is another improvement, because it means that they only need to be honest at the start, and if they turn malicious halfway through, there's not as much that they can do. So that's one thing. Yeah, another thing is that we can have so before we talked about what would happen if the journalist or the operator, the owner, was malicious. And now let's talk about what if the other members in your group are anonymous, or are malicious. Because the other members in your group are kind of what protects you. Yeah, because they're your anonymity set. But unfortunately, they're able to prove if they took an action or if they didn't take an action. So, number one, that means that it's possible for us to bribe them. So we could bribe the members of the group we could bribe them to sort of lie and say something that's not true. Or we could So let's imagine that one of the members of this group said something that's very sort of controversial, and other people come forward and say, okay, we want to find out who said the controversial thing. So they would then go to all of the members of the group and say, you have to prove that you didn't say this controversial thing. Yeah? And so every time someone proves that they didn't say it, that reduces the anonymity set. And the only person who will not be able to prove they didn't say it is the person who did say it. So that's another problem. And there's some ways that we could fix this. So one is that the journalist could keep the members of the group private, but that kind of means that they're vulnerable to this this kind of attack where they're all partitioned in their separate tree. So that the two attacks, the attacks kind of, it's kind of a trade-off here between which attack you want to be more vulnerable to. You want to be more vulnerable to the members of the group turning against you, or you want to be more vulnerable to the journalist turning against you. Yeah, so that's one way we could solve it. That's kind of, yeah. Another way is that we could have the users update their public key every epoch and delete their own public key. And the idea is that, imagine that one of the groups says something that's controversial, and then some group goes to all of the people and says, oh, this is not your public key, or prove that you didn't make this signal. And then hopefully the members of the group could justifiably say, I can't prove that I can make that signal because I deleted the private key, the public key. Yeah, that you could update the tree every sort of epoch with a new public key. But the problem with that is that it's very expensive to do, to update the gas, to pay the gas to do the updates. And another problem is that some members mightn't do it. Yeah. So, yeah, that's a problem. Okay. Okay, so let's talk about the second sample application, which is anonymous DAO. Yeah. So we have a group of people, and they want to be able to tell a smart contract to do something. Yeah, they want to kind of have these sort of votes about what should we do with this money, where should this money go, or something like that. They want to control a registry, something, ENS name, just some example of some Ethereum thing that you want to do. So, but they don't want to reveal to anyone what their actions they are supporting. So they want to vote about how to spend some money, but they don't want that to be public information. But they're happy with all of their actions eventually becoming public. Like the actions of the group become public, but the actions of all the individuals are private. So how do we do this? Yeah, so we take the journalist from the previous example and we remove her, and we replace her with a smart contract. And we still have our same group of people from the organization. So these are the people that are going to be running our let's call it a charity. Yeah, so they all have a single vote in our charity, and they're trying to decide how to spend X amount of money. So we have to have two things in our, so there's two things that we use a snark for, and then everything else we just do in the EVM. Number one we use a snark for is to create a new poll. That's just to say, oh, I think we should spend the money here. Or spend some of the money here. And then the other thing they need to do is be able to, Yeah, the other thing they need to do is to be able to vote. Okay. So how does the first one work? So every epoch, every user is able to create a single poll. Yeah. So the epoch can be like 1 day, something like that, 1 month, depending on how frequently you want to create these polls. So how do we enforce this? It seems like this might be a difficult problem because sorry. Yeah, it seems like this might be a difficult problem because it's difficult to attribute an action of a user to limit them from doing something that they. Yeah, if everyone's anonymous, it should be impossible to tell if someone is making an action twice. But it turns out we can use the nullifier system that we used before. Maybe I was. Yeah. So we can use the nullifier, the signal and the nullifier, and I'll explain that on the next slide. So what we do is we say, for every new poll, we change the external nullifier. So for every unique external nullifier, the users are able to create one single valid signal, only one. So every time we change the external nullifier, we kind of make a blank slate, and anyone is able to come forward, any member of the group is able to come forward and make a new signal that's totally unlinkable to all of their previous signals. So, yeah, so what we do is we include that in our external nullifier. Yeah, so we need to do two things here. Number one, we don't want the external nullifier from this function affecting the external nullifier from the second function. So in order to prevent that, we put this kind of new poll just at the start of it. And then we have the nonce. And the nonce is like the epoch that this poll is from. Yeah? So let's say that once every month we make a new epoch and everyone can come forward and make a new proposal. Yeah? So we increment that every month. So anyone can call a new vote with a new signal. And this is in the smart contract. So anyone can call the smart contract and provide a snark proof. And when they call the smart contract, the first thing they do is they validate the snark. And then they check that the nonce was not, they check that the nullifier was not used before. So this is the nullifier right here, the hash of the identity commitment plus the external nullifier. So every time we update the external nullifier, this becomes something new and different. So we say this, so we need to check that this wasn't used before. So when we do that, when we confirm it wasn't used before, then we save it so that it can't be used again in the future. So we check it wasn't used before, we save it. Yeah, then we check that the external nullifier is equal to the right, is calculated correctly. And this should be poll, not vote. No, this should be poll, not poll. Or something like that. No, this should be poll. This and this need to be consistent. Yeah, that's really important. Otherwise, it's just a different external nullifier. Yeah. Okay, so then after all of that is done, the new vote is stored and the voting begins. Yeah. So how do we do the voting? So we do the voting in a very similar way. So count vote should probably be include vote, but anyway. So we do the voting in a very similar way, but we just need to change the external nullifier. So we change the external nullifier to be the poll ID, the vote ID. So every time we create a vote, we make it and we increment the counter of votes, and we just set that to the new vote count. So each vote poll has a unique poll ID. So we use the poll ID as an external nullifier. So we include that. So we set that. So we validate the snark, and then we check the poll ID is valid. And then so the external nullifier defines the poll, and the signal defines yes or no. Yeah. So at the moment we kind of have just this binary option here, but we can kind of hack around with this and come up with other ways to do it. So we check that the nullifier has not been used before. Yeah. So then the user creates a proof. They broadcast a proof. So we validate the proof, and then we check that the nullifier has been done before. Then we store the nullifier so it can't be used again, and then we count that vote. We just include that vote in the total number of votes for this topic. Yeah? Okay. Alright. So, yeah, so now we're starting to have, so now we have this kind of anonymous DAO where we use snarks to make these signals. And everything kind of works. But then we need to do some kind of housekeeping. We need to add stuff for everything else. We need to be able to execute a poll once it's finished and things like that. So then there's just all this other smart contract functionality that we don't need to talk about because it's not specifically snark stuff. I mean, this is just regular smart contract stuff. So you just have a way to execute a vote, you have a way to add members to the group, you have a way to send funds there, you have a way to set the epoch, set the rate at which people are able to create polls. And this is all done in smart contract, there's no steps required. So we kind of just gloss over this for now, although it's probably a difficult engineering problem. It's not really in scope for this talk. Okay. Okay, so this is the third sample application, and this is a mixer. So just a little bit of background for people who are kind of newer to the space. In Ethereum and in most blockchains, every single transaction is validated by every single member of the network. And this is a problem because that means that every single transaction has to be public. So every transaction is public, and you can trace the entire history of every coin in most blockchains back to where they came from, where they were mined. So blockchain is like Twitter for your bank account, people say. Yeah, because everything is just completely public way. Although some people, so there's a lot of talk sometimes in the media about blockchain being anonymous. This is not true. It's kind of pseudo-anonymous, and that means, I think that means that you can just create an address out of nowhere. So so people say that, oh, it's difficult to tie this address to this identity, but there's some problems with that because if you send me money, I can tie that address to your identity, and I can also do some analysis and see where the money for that account came from, and I can trace it back and find out just more and more information about what's going on, where the money came from. Okay, so anyway, we want to make a mixer so we can have like anonymous ether, just to be able to get some gas money to do to buy some gas, to broadcast some transactions, to deploy some contracts, to do some stuff like that. Because a lot of times you just want to play around with things and you don't want everything to be linked back to where it came from. So we need to be able to do three things. We need to be able to do two things. We need to be able to deposit ether and withdraw ether. Yeah, we want there to be no links between the deposit and the withdrawal. Okay. Cool. So let's start again. So we have our group of people, and we have our group, and we want to be able to add people to this group. So we have a smart contract that adds people to the group, but in order to be added to the group, we have to send X amount of money to the smart contract. Yeah. So you send one ether to the contract, and then that lets you join the group. So this woman sends one ether to the contract, and she's in the group. Yeah. All right. So she joins the group, and what happens next? So that's the deposits working. Deposits are working. Everything's good. We don't have to have a start for this at all. It's just a hash function inside EVM. Cool. Okay. So when the deposit happens, we check that the balance is correct. So we say that, you can only send one ether and you can only withdraw one ether. So we check the balance is correct, and then we just add the leaf to the tree. So we check the balance is correct, and then we just put the leaf in the tree. But to withdraw, it's a little bit more tricky. So we have to validate the snark. We have to check the nullifier is not in the tree. Yeah, because if the nullifier the nullifier is not saved. Yeah, if the nullifier was not already saved, if the nullifier is already saved, that means that transaction is already being processed. So we should reject it. So we check the nullifier is not in the tree, and if that's true, we continue. Then we add the nullifier to the tree, and then finally we send the funds to the person who requested. Yeah. So yeah, there's some. So this is kind of simpler application than the first two. It's just money goes in, money goes out. So there's some things that we need to do here. One thing, the big kind of thing that hasn't been done is the gas abstraction. So we should have someone paying the gas. So for example, I want to withdraw my ether from the contract, so I create the snark. I nominate a broadcaster. I send that transaction to the broadcaster. They broadcast that to the network, and my transaction gets included, and the money gets sent to me. So that should work. But the broadcaster, but you need to have privacy for the broadcaster. So it would be good to kind of wrap this within Tor and use some kind of peer-to-peer mechanism to limit how your transactions can be linked to you. Because otherwise the operator would know which IP address made which request. Yeah, so that's one thing that needs to be done. Another thing is the smart contracts to handle the deposits and the withdrawals. That's mostly working, I think, but there still needs to be some work and testing and stuff like that. The user interface we need to do that too. And then probably, so at the moment we use MIMC, which is a hash function that's specifically designed to be very efficient inside a snark. And it happens to be pretty efficient inside the EVM. We would probably prefer to use Pedersen commitments because that's kind of a more secure hash function that's being tested a lot more. But unfortunately, that's not very efficient inside EVM. So that would mean that our deposit step would be a little bit difficult. We would probably have to include a snark in the deposit, which kind of hurts. I mean, it's just a little bit annoying that you have to do a snark there too, because you have this kind of raise condition when people are trying to deposit. Yeah, so two people are trying to deposit, and it's whoever is quickest to broadcast the. Sorry, hold on, let me start again. So two people are trying to deposit, and both of them calculate their snark based upon the current state, and only one of them is going to be able to update the state, because the other transaction will become invalid if they're coming after the person who's currently there. So we have to have a way to kind of batch them together and then do deposits, which just adds complexity and it's annoying. But we'll probably end up doing it unless we get this IPI. Oh, that should be. That's not the right IPI at all. It's 1962. Oh no, this is 1829. No, this is the right IPI. So if 1829 gets included, that would really help because that allows us to do Pedersen commitments. And actually, 1829 should be there. It should be 1962 because 1962 kind of supersedes 1829. It includes some other things as well. So this would help us with the Pedersen commitments, which would be pretty cool. But if we don't get that, we can still do it. It's just going to be a little bit more annoying, or it's going to be a little bit more complicated. Yeah. Cool. Okay, so now let me talk a little bit about the privacy set. So, okay, so here's what's happening here is a deposit in the mixer. Okay, so at the moment there's 3 people who have deposited coins into the mixer. Someone does a deposit, and then the new set becomes 4 people in the mixer. So these people have question marks on their faces because we don't know who they are. We know who the depositor is, we don't know who the withdrawer is. So this actually should be kind of transparent, but I guess I'll fix that later. Yeah, so every time someone deposits, our privacy set gets bigger. Yeah? And we always know the size because we always know the number of deposits, right? Because deposits are in public. So as time goes on, more and more people join our set and things get more and more private. And then, okay, let's imagine somebody withdraws. So now what we have is 3 people in our set. 1 person withdraws and now we have 2 people. So on the withdrawal we don't know who did it, but we do know it has to be someone who was already in the set. So if the set is really small, then we don't really get a lot of privacy about what's going on. Like, for example, if there's 1 person in the set and they withdraw, we know exactly who withdrew. You know, there's no way to, there's no privacy there. So one thing that we need to be careful about is the size of our anonymity set. So we want to maximize this. But this is kind of a problem because in Ethereum we have a whole bunch of different tokens. Yeah, and if we want to include privacy for all of those tokens, it's kind of difficult because we have coin 1 and coin 2, and there's only 1 or 2 people in there. These tokens are liquid and not a lot of people hold them, so it's difficult for them to have privacy. But we have other tokens like ETH that a lot of people hold, or comparatively a lot of people hold. So for small cap tokens and for illiquid tokens, it's really difficult to have good privacy. So how can we overcome this? So one thing that we could do is that if we were able to do like atomic swaps inside the mixer, then we could do like trades inside the mixer. So let's say that I have token 1 and you have token 2, and let's say that I have token 1 and you have ETH inside the mixer, and I want to be able to kind of hide my owning token 1. So what I do is I go to the mixer and I make a trade, or I publish like an order, and I broadcast that order to a bunch of people in the order book, and the people in the order book say, someone comes forward and says, oh yeah, I'll match that order, and they send me the other side of the order. So my order is a snark proof that I hold these coins and I want to make this trade, and the other person's order is a snark proof for the opposite side of that they hold the other coin and they want to make this trade. So then what we do is we combine them together, and one of us makes a snark proof, that this is all correct, and we broadcast that to the smart contract, and everything, and the transaction happens. So this will really help us when we have these smaller tokens that we want to have anonymity for. So this is something that we were thinking about doing, but we need to be able to do like recursive snarks. We need to be able to validate a snark. Inside snark, we need to be able to validate a snark. And this is possible, but we need to do a hard fork for it. So we need to do EV 1962, which is also proposed. So that would really help us there. If we could do that, we could also do like smart contracts inside rollup. That we could have privacy inside rollup, and we could also have smart contracts. So basically, we could come up with an idea which is like pay to public key, where you have a snark public verification key that the money gets sent to instead of an account, and you can only move the money from that account if you validate that snark. So we could do things like that. I can talk about that a little bit later, but I don't really have any slides about it. Yeah. Okay, cool. Yeah. So here we talk about the anonymity side. So this is similar. This is similar to Zaxi, which is a paper that was published last year, I think, that talks about doing this too. Yeah, and that lets us increase the anonymity set. So one good criticism of that idea is if you say, oh, but really you're revealing the coins that you have when you make the order, right? Because you have to broadcast the order to everybody. Someone can just monitor all the orders, and they should be able to find out whether your transaction was included. They should be able to find out what your balance is based upon what your orders are. Or they should be able to come up with like a set of transactions that happened in the past. So one thing that we could do is we could use like an NPC scheme in order to encrypt the order in such a way that only someone who's trying to execute the opposite side of that order is able to decrypt it. Yeah. So we can have this kind of cool NPC kind of dark pool thing that we can do, or we can So one thing is we can have an NPC with like multiple parties, and the other idea is we could have an NPC between just two people. That every time I would just go on chain and advertise to everybody, hey, I want to make an order. Who wants to match my order? Without revealing anything, and other people can come back and say, oh, I want to match your order. And then we go through this kind of two-party process whereby we don't reveal any information about our actual orders unless the other person is trying to fill the opposite side of that order. So we could do this cool NPC thing.
If atomic swap is available in the mixer, that means that the anonymity set of token 1 and token 2 can combine to one anonymity set?
So it kind of depends. It depends how long. So the question is, can we combine the anonymity sets together if we have these atomic swaps inside the mixing? And
the point we want to allow the trade, or is that the reason we want to allow the trade? Or?
Yeah, so that's the reason why we want to allow the trade. Yeah. So I don't know if I can make that claim completely. I think we'd have to do some analysis. So my instinct is yes, that's true. And in practical sense, that should be true. But we still, it should be true because, okay, let's look at it this way. Let's say that a transaction comes to take Ether out of the smart contract, and we want to find out what deposit made that. So originally, in the previous system, we would have the set of all Ether deposits. That would be the only way that we could that money could have gotten there. But in this upgraded system, we could have a set of all these deposits plus all the other deposits combined. But we would have to include some kind of market mechanics. We would have to think about, we would be able to exclude tokens tokens whose volume was less than, tokens whose volume and price multiplied together were less than the price of Ether at that time. Yeah, the idea is that you would assume that no one is selling their tokens at a loss. So, okay, for example, let's say that someone withdraws 1 Ether from the smart contract. Yeah? And I make a list of all the transactions that went into the smart contract, and I say to everybody, listen, these are the deposits these are the only deposits that could have been linked to this withdrawal. But someone could come along and say, oh no, but look, there's a lot of one guy deposits here. There's no way that one guy deposit was turned into this 1 Ether withdrawal. So there's ways that you can like limit the set that way. You need to be within, yeah. But another thing that we could use is we could allow merging of different balances. So then, but then that doesn't really help us so much, because you would say, yeah, so it could be like these 200 1 Ether or 1 I deposits could equal this 1 Ether withdrawal. Yeah, so there's nuance there, but yeah, I think roughly that's right. I'd like to see some more analysis of it. Like, for example, there was some really interesting done analyzing the Zcash blockchain, where they tried to find a privacy set, or they tried to just de-anonymize some coins based upon just some simple heuristics that they came up with. So one of the simple heuristics was, the last deposit is this withdrawal, and the idea is that people would just deposit their money and then instantly withdraw it. Yeah? So when they instantly withdrew it, it doesn't really give you that much privacy. Yeah, because, I mean, that's just like one useful heuristic that you can use. Another problem with what was going on is that people would deposit like a strange balance, and they would withdraw that strange balance later. Like, there was a lot of 1ZC deposits, and there was a lot of 1ZEC's withdrawals, but there was very few 0.135621 deposits, and there was very few withdrawals. So when you have these variable amounts, it can also help de-anonymize people. So these are things we need to be careful about. Yeah. Cool. Okay, so we can also do the same kind of privacy inside ZK rollup, and then will be ZK rollup. And I think the Vitalik talk spoke pretty recently about this here. Yeah, so basically we would do the same thing. We would have a snark inside snark, and we would use the internal snark we would use instead of the signature. And then we would have to do some kind of weird stuff. We would have to have like an accumulator that can do proofs of non-membership, and we would store the nullifier there. And then in order to make a transaction, we would just prove that is not included in the accumulator, and then we would include it in the accumulator, and things like that. Yeah, so, okay, so conclusion. So, pretty much done. How long was that? Okay, so, let me do the conclusions. So, Semaphore is pretty much ready for people to start working on. I mean, at least the smart contract is, or the circuit is, but the smart contract and the user interface and the P2P stuff is not really ready yet. And that's places where we're actively soliciting help and looking for people to help. So there's some ideas here, but there's a whole bunch of other ideas as well. It's also, I think this would be a good project to sort of get involved with ZK Zero Knowledge Proofs and to start to think about building things with them. Because it kind of starts off just being like heavily about smart contracts and networking and user interfaces, and then it kind of transitions to doing more snark implementation stuff. So here's the link to the code. Kobe is there. And here's a Telegram group about where we talk about this stuff. So if people want to join, Kobe's in the group as well, so he's happy to help and answer any questions that people have. Yeah, that's good. So, okay, thank you. I just want to thank Kobe. First of all, he did great work putting all this together. And Harry and Jordy for sort of helping out in the earlier days, sort of thinking about these ideas and doing a lot of work to do proofs of concepts and getting things working, fitting together. And the Zcash team for kind of really pushing these ideas forward and just kind of pioneering this kind of work. Okay? And I have some more slides. I can answer questions now if you like, and we can do the demo, or we can do the slides, whatever people want to do. Yeah, so is there any questions?
So is the Snark, because you mentioned Snark is not in the EVM, so is it something not in, like, coded by Solidity, or is it, so, like, yeah, that's my question.
Okay, so what happens is that the snark is validated inside the EVM, but it's not defined inside the EVM. So we have a whole bunch of different languages to define snarks. One of them is Circom, which we use in this project. Another is Locrates, which is a DSL screen language. Another is Bellman. Another is XJSnark. There's JSnark. There's Coda. There's a whole bunch of different languages that you can use to define. There's EdSnarks, a whole bunch to define these different different circuits. Yeah? Okay, so if there's no questions, let's do the demo, because maybe that will kind of stimulate some more questions. So just give me 1 second, let me open my browser.